This production is brought to you by the University of Edinburgh.
So that was a broad introduction. So let's actually get on to signal processing. When you're going to learn, put the PDF of the notes online. It's actually got links to some YouTube videos embedded in the lecture notes. So this is the kind of thing that I'll sort of put onto the social media page as a YouTube link. But if you open the notes on Learn in Adobe Acrobat, then you can click on the links and it plays a YouTube video if you've got an internet connection. So that's quite good. So there's a nice little video. It's an American video from the IEEE. It broadly describes what signal processing is. Basically, signal processing is a branch of electrical engineering. Some people might think, oh, isn't it informatics or computer science? And the answer is no, it's part of electrical engineering. And I think the reason for this is to stand back and think about the chain from the real world to an electronic device which does something. So the chain from going from a real world to an electronic device needs a sensor. And that sensor could be a microphone, as I've got a couple on. Yeah, it occurs to me that I've got a radio mic for this room, but I don't know if it's working. But I've got two on, one to record the lecture and one to play back. The fact that I'm wearing two radio mics clearly shows that there's a long way to go with regards to sort of improving audio-visual topics. But you've got to measure a real-world signal. That's what we do. There's something in the real world, we want to observe it. Now the trouble is, there's a bit of sort of, if you like, quantum mechanics in this. If you ever observe something, you're never observing exactly what you want. You're always measuring it either at a distance, or you're measuring it through a distortion through a channel. So Popular on Tuesday talked about the fact that the room acoustics is a channel. So as I speak to you, you're not actually hearing the same signal that my microphone is picking up. You're getting multipath propagation, and you've got background noise. And if this room were bigger, then it wouldn't be a particularly high quality signal that you're measuring. In fact, if anyone were trying to record this lecture on their iPhone, in fact, I might encourage you to do this next lecture, record it on your iPhone where you're sitting and compare it with the quality of the audio that you get through a radio mic, and you'll see that there's a massive sort of perceived difference. So the fact that you're always measuring something at a distance means that the signals that you get at the output of your sensor is not what you want. It's got noise, it's got distortion, so you need to do something with that signal to improve the quality of it. So if you measured this lecture on your iPhone and you've got background noise, background reverberation, you need to try and suppress that noise, and you need to try and remove the reverberation. Now, there are a variety of techniques for doing that, and throughout the lectures I'm going to give you various demos and examples and explain how you can do that. But the manipulating of a signal that comes out of a sensor to get what you want, that's what signal processing is. So the output of your sensor, just to check, are any of you sort of E&M students, or you're all straight electrical? Okay, so I think you're all straight electrical. Because it's straight electrical, then you'll be getting, most of your signals will be electronic signals. Obviously, it is possible to do signal processing with optics, and it's also possible to do it with mechanics. So all your signals are electrical, the output of a microphone, the output of a camera, the output of an ultrasound machine, all need cleaning up, and that's what it is. Now the applications of that are everywhere, and it's a question of sort of thinking about applications and thinking, is there any signal processing going on? So obviously there's modern communications, that's what Popular discussed, but we've also got entertainment, and we'll try and give a demo. When I say entertainment, I mean basically hands-free human-computer interfaces. So can you control a device without having to actually touch any sort of particular control input? So we're going to use camera sensors, depth sensors to try and work out, sort of the classic thing of, do a swipe to change what pictures on your television. So if you've got one of these sort of smart TVs with a little sensor, I don't know what the gesture is, but that would be one example. Or if you're just playing a Wii, then obviously, just practice my forehand is, detecting that motion very smoothly. Transportation, I mean, automated vehicles is a classic example of an area which uses signal processing, machine learning, and informatics. Yeah, autonomous vehicles. What a fantastic area to be in. So if you get a job with Google and you're trying to develop a self-driving car, obviously the self-driving car is going to use computer vision because it's trying to detect objects within the scene. It's going to try and detect pedestrians, but it's also trying to detect obvious things like curbs, road markings, and so forth. Now, the object recognition is technically sort of part of an area called machine learning, and machine learning is part of informatics. However, there is a massive overlap between informatics and signal processing. One of the things is that a lot of the signals that are coming from an autonomous car are very incredibly noisy. So one of the things it might use is something called LiDAR. LiDAR is like radar. So radar sends out signals, radio signals, bounces off metallic objects, comes back at you, and that allows you to work out how far that metallic object is away, how far away it is. But the trouble with that is that these measurements are, if you saw the raw measurements, you'll just be like, whoa, how do I manipulate that signal? LiDAR does the same thing, but LiDAR does it with a laser. So you point a laser at something, you get reflectivity from a wall, tells you how far away it is. You can also do it with infrared, so when I show you the Kinect in a while, the Kinect uses infrared to get depth. These signals are very, very noisy, and you have to try and enhance them in some way or try and process them. So autonomous vehicles, I mean, that's a fantastic area to work in. Now, all of these problems are going to be solved by writing algorithms that are implemented in software, that are implemented on either a DSP or, I guess, FPGA, and they're going to, it might be a dedicated implementation on a very low power device, or it might be something that's churning on a supercomputer somewhere. Okay, but writing it in software and trying to implement it in hardware, that's something which you're going to cover in other courses. This course is a concern with the algorithms. How do I take signals and how do I manipulate them? The other one is healthcare. Healthcare is, I mean, sort of, healthcare is one of these areas where I just wish, more students would go into. So you sort of think, healthcare, what do you think? Doctors, surgeons. But what are the tools that doctors and surgeons use? Well, they use, the first thing that you probably do when you go into hospital is, well, you could go and have an x-ray, but more recently you'll be doing MRI imaging, medical resonant imaging. Or you might go for a CT scan, or you might go for a PET scan. Now all of these are physical, obviously the physicists help us sort of create some of these technologies, but the outputs of those sensors are very messy, and they need to be manipulated and they need to be improved. And the images that are reconstructed from these very complicated sensors are then given to the doctors who interpret them. So sure, yeah, doctors and surgeons are incredibly important, but this stage before is equally important, because if we didn't have PET scanners, MRI scanners, you wouldn't be able to sort of track the growth of a tumour in someone's body. And if you can't track without doing an invasive procedure. So if you want a non-invasive procedure, you need to image them, and that's an incredibly important area.
This production is copyright the University of Edinburgh.